Does that answer the question?
Yeah, that was very nice. Thank you.
Okay, so I think with this, let's give thanks again to Ruslan. We'll switch to the next talk. It will be a remote talk being presented by Daniel Roten. He's the head of the scientific computing platform at the Friedrich Mischer Institute for Biomedical Research in Basel, Switzerland. His research focuses on HPC, scalable workflows for big data processing and machine learning. At the San Diego Supercomputer Center and San Diego State University, he integrated nonlinear rheology and a discontinuous mesh into the AWP ODC, which is a highly parallel GPU accelerated solutions. So let's, I believe, Daniel, you will be presenting, not Yifeng, am I right? Is that?
Yes, that's right.
Okay, okay. So let's then very quickly move to the talk. Daniel will be talking about optimization of a finite difference wave propagation code with GPU or MPI support using MVAPICH2. So let's welcome Daniel.
Thank you, and thanks for the introduction. So in this talk, I will present the AWP finite difference code for wave propagation, which has been mentioned already a few times. And I want to focus a bit on the improvements and features that were added in the last couple of years, but also provide a bit the big picture of why we want to simulate earthquakes and why this is such a high performance computing problem where we need message libraries such as MVAPICH. So the motivation to simulate earthquakes is really to understand and predict wave propagation effects that lead to strong shaking and damage. So those simulations don't predict when or where an earthquake would happen, but it can provide some insights into amplification by soft sedimentary deposits or wave propagation effects such as a source star activity that can really increase the ground motion. So this is a simulation that we performed with AWP a couple of years ago. So it's called the Shakot scenario, and it features a large magnitude 7.8 earthquake on the southern San Andreas Fault. And you can see here, so the source starts under the Salton Sea and propagates towards the northwest, and you see the source star activity effects that is channeling waves towards Los Angeles and into the deep basins in that area. And you see how those basins amplify the ground motion and lead to stronger and longer duration shaking. And you see also in the simulation the green areas, which indicate permanent plastic deformation, which reduces the ground motion, which is also something that we introduced in the code a couple of years ago. So I want to give a short review of the milestones that were done with this code and the features that were added, and especially the computational challenges with respect to crunchy numbers and also communication that arose from those extra features, in particular plasticity, where we have two different models. And I will also show milestones and benchmarks done on a recent accelerated system and done with MVAPICH. So what makes earthquake simulations a high-performance computing problem are two things. So the first one is the large scale that you need to simulate. So the seismic hazard is really dominated by earthquakes that occur on large faults, which are large magnitude earthquakes. And that requires a large computation domain to include the fault and all the surrounding areas. And the other thing is the resolution that is required. So in the past, those simulations were done at low resolution, and only they captured the long wavelengths, which are only relevant for very tall buildings, like high-rise building with 20 or 50 floors. But the most vulnerable buildings are much shorter. They have 2 to 5 floors, and they have natural frequencies of 2 or 5 hertz. And to capture that, you need much higher resolution. And only recently we've been able to go to the resolution that is required to capture those wavelengths for really large earthquakes. Another challenge with going to those higher frequencies comes from the physical effects that dominate at the frequencies above 1 hertz, and in particular topography, scattering, and plasticity, which can happen near the fault or near the surface, which was the focus of my research in the past. So AWP started as a personal research code developed by Kim Olsen in the 90s. It solves the 3D velocity stress wave equations by an explicit staggered grid fourth order finite difference scheme. So in the 90s, inelastic relaxation was introduced with the memory variable formulation. Later in the early 2000s, the code also added support for dynamic rupture, which means that the earthquake source is not prescribed, but it really evolves as the solution to an elastodynamic problem, which is also important. It supports different types of absorbing boundaries, which are required like in any finite difference wave propagation code. So originally the code was a pure CPU MPI code for early clusters. So it was one milestone simulation done in 2010 with that code, and it just uses geological domain decomposition to distribute the workload over different CPUs. Then in 2012-13, he added GPU acceleration, and that version was a lot more advanced, and not only was it faster, but it had a very elaborate, clever communication and computation schedule. So it basically overlaps the computation with communication. This is done by first updating velocities in the border regions, and then doing the communication while velocities are updated in the center of each subdomain. And the same is then done with the stress while the velocities are being updated in the east and west side. And that way, the GPU is always busy. And this early code already had excellent scalability. Back then, this was in the system OLCF Titan, where it had more than 99% efficiency on thousands of GPU nodes. So when we implemented nonlinearity in this code, we had a few challenges. So nonlinearity means that you are deviating from the linear stress-strain relationship. And in the simplest model, the material just yields when it reaches a given yield stress. So the problem with that, you need to know all the 6 independent elements of the stress tensor to evaluate the Drucker-Prager yield stress. And the mesh is staggered, which means that the stress tensor components for normal stresses are stored at a different grid position, offset by half a grid point from the shear stresses xy or xz or yz. So when you want to evaluate this criterion, for example, where the normal stresses are defined, you just have to interpolate from nearby grid points, which is not at all complicated, but it just becomes computationally expensive. So in our first implementation, we just individually interpolated the stress tensor elements at each location where the normals and the 3 shear stress tensor elements were defined. But with that configuration, the code was about, nonlinear simulation was about 4 times more expensive than a linear one. So what we did instead, when figured out that when you apply the Drucker-Prager yield condition, you actually establish a yield factor called R, which tells you by how much the stress deviator yields. And we only computed that at the position where the normal stresses were defined and interpolated only this yield factor for the other subgrid positions. And we found that for a scenario simulation like the shakeout I showed before, those 2 solutions are basically indistinguishable. And with that solution, the computation cost of adding plasticity is only about 65% more than a linear simulation. And we then ported this code to the GPU version, and there we ran into the problem that, especially in those early GPUs, memory was very restricted. But nonlinearity requires a lot more 3D arrays than linear simulation. So a linear simulation had 22 arrays, while the nonlinear one had 17 more. And this really greatly increased the need for memory in our early implementation. And we did instead, we just compute memory for flops and just recompute a lot of those parameters which are needed during each stress update on the flight during each iteration. So this only slightly increased the computation time from, in this case, 54 to 55%, but it saves quite a lot of memory. We figure there are some parameters that are more expensive to calculate, so we prefer to just keep them on the memory to just have a good trade-off between compute time and memory use. And when we implement the plasticity, we also had to rework the communication and computation schedule, which becomes a lot more complicated in this case. So the stresses were in this case first updated at the border region, and we started doing plastic computations again in the border region, while we still keep updating the stress in the central region of the subdomain. And then those yield factors R that I mentioned before, they're being swapped with adjacent subdomains, and this happens also while the stress update is still going on. And then when you calculate this yield factor in the center of the domain, you swap the yield factor in the east and west sides. And then finally, once the yield factor is known everywhere, you can just reduce your stress tensor everywhere in the computation subdomain. And using those optimizations, we actually managed to preserve the scalability of this code down up to several thousand GPU nodes on a Titan using both, also with nonlinear simulations. We then used this nonlinear code for some important earthquake scenarios. The first one was the shakeout scenario I mentioned before. So those maps here compare the peak ground velocity in the Los Angeles region to the left for a linear case and on the right for the nonlinear case. And you can see that those velocities are being significantly reduced once you account for plasticity. The amount of reduction depends a bit on how you specify those nonlinear parameters in the model, but it can range from 30 to about 70% with respect to linear models. Another scenario that we simulated with the plastic code was the 1991 Landers earthquake. So this earthquake, for this earthquake, the fault state was mapped both by geologists in the field, and it was also established from satellite INSAR observations. And what was found is that only a small part of the deformation happens on the fault itself, and there is at the surface. And at depth, there is more deformation happening. That means on the surface, you're getting kind of a finite fault zone where the deformation happens. And some researchers like Milner and others, they quantified this off-fault deformation, which is defined as the total displacement minus the surface displacement normalized by total displacement. And they found that it's about normally distributed with a mean of 50%. And when we simulated this earthquake with a linear code, we obtained off-fault deformations of less than 10%, which just doesn't match the observations. But once we added non-linearity, we actually found, depending on the rock strength, we also get this about 40 to 50% off-fault deformation, which is somehow an independent observation confirmation that those nonlinear models are more realistic than the earlier linear models. Another feature that we introduced after plasticity was a discontinuous mesh. So I mentioned before that we need to sample the wave field at high resolution at the surface, and that's because the seismic velocities are very low close to the surface. But at greater depth, the speed of the seismic waves is much higher, and you're basically oversampling it if you use a uniform mesh down to your entire depth of the computation domain, which is can be 20 or 50 or 100 kilometers. And one way to fix that is just to have a discontinuous mesh transition. In our method, the mesh size increases by a factor of 3, and there is a transition zone with well-defined arrangements of grids and routines that takes the wave field from one grid and just translate it to the coarser mesh below. One challenge with these discontinuous meshes is numerical stability. We experimented with different filters, and we managed to get that stable using a 3-dimensional lens filter. And so we are actually able to get that stable for most of our production simulations. It can still be unstable when there's a sharp contrast or a water solid transition inside this discontinuous mesh transition zone. In that case, you just have to tweak the depth. But we are able to use that now routinely, and we also verified this against the uniform mesh. So we simulated the 2014 magnitude 5.1 La Habra earthquake, And we assume that we know that uniform mesh solution is the correct one, and we compare that to a solution we get on the discontinuous mesh, so shown here for one station where the earthquake was observed. And you see that both solutions are indistinguishable, both in the time as well as in the frequency domain. And in this case, we used the 2 transition zones, so twice increasing the grid size by a factor of 3. And the simulation with the discontinuous mesh only used 12,000 node hours on the system OLCF Titan compared to almost 100 node hours with a uniform mesh simulation. So that's a very significant performance increase. And it's actually even more than that when you go to greater depth with your computational domain, which is something we often do for large earthquake simulations, where we go sometimes to 150 kilometers depth or more. So the next improvement we worked on was a multi-surface nonlinear model. So the J2 or Drucker-Prager plasticity I mentioned before is very simple. So in that case, during loading, the stress-strain relationship stays linear until you reach the yield stress, in which case it becomes flat. And this is not really the behavior that you observe, especially from soft soils during lab measurements, because those tests show that it's more a gradual reduction of the shear strength until the material yields completely. And this is actually more tricky to capture numerically. But one way to do it is using a method called the Ivan model, or also overlay principle. And it works by combining a series of Drucker-Prager yield surfaces, which then approximate the more complicated behavior. And the way to think about that is for a simple 1D model, where you just apply shear in one direction. You can think of the material as being a combination of springs and sliders, with each slider having a different yield strength and each spring having a different strength. And as you start deforming this material, those sliders start to yield one after the other. So when the first one yields, the slope of this curve is slightly reduced because the strength of the material is just the sum of the remaining springs that have not yielded yet. And you can basically piecewise linear approximate this complicated nonlinear backbone curve. And this is what you're doing with the Ivan model that we have implemented in AWP. So this is computationally expensive. So you're not just looping over a number of time steps, but for each time step, you have to loop over a number of yield surfaces, where each surface has its own material parameters and its own, like the shear modulus and bulk modulus, and also its own yield stress. And those parameters are also computed on the fly, just to conserve memory on the GPU. And once you're done with that, you basically just compute the overlay stress, which is the sum of all the stress tensors, and use that to update the velocity. So this is actually quite good in terms of communication, because you only have to swap one yield factor for each surface, but it's not so much data. So that's why the scalability is still quite good. And we actually verified the implementation of this model. We know from engineering seismology, there are a lot of 1D codes that use the same model that have been verified against each other. So one of those codes is called NOAA, and was used to simulate response of one Japanese kicknet site. And we can actually change our problem from such that it can be used to model a 1D problem by just using periodic boundary conditions and a laterally homogeneous medium. And we get a very good match with the NOAA code, which gives us confidence that this is implemented correctly. For the 2D case, there is only one code we can compare against, the 2D version of NOAA. So we use the generic segment-filled value for that. And you can see how nonlinearity reduces the length of the reverberations inside those basins on the left side compared to linear to the right. And we also get a good match with the NOAA code. So unfortunately, there is no other 3D code that we can compare our results against yet. And so now, once we knew that this is implemented correctly, we modeled the shakeout scenario again, but this time using a realistic multi-surface Ivan model. And we found that the ground motion in the Los Angeles basin is reduced even further compared to a simple J2 Drucker-Prager yield condition. And so the waveguide effect can be almost eliminated if the material is very weak. And what you can also see in this simulation is the minimum shear modulus normalized by the initial shear modulus. So that you can see from those greenish colors that the shear strength can be reduced by almost a factor of 2 in the Los Angeles basin. So you get only a few colors because there's a limited number of yield surfaces, because the shear modulus degradation is being approximated by this step function that you can see in this little diagram. But that's another challenge, because those reductions reduce the highest frequency that you can resolve with your simulation. Another recent development was porting of the AWP code to AMD GPUs. This was done using the HIP protocol, and there's several versions of AWP that were ported to this system to run on a Frontier, for example. So there's the Strain Greentens SGT version that is used for Cybershake, which is a project to produce physics-based seismic hazard maps. This was ported and verified. The linear version, the version with topography, was implemented and verified, and the Ivan type London model still being implemented and verified. And this was actively used in production simulations and inside and OLCF DD awards in recent years. So there was an award of 700,000 node hours. And there was also a weak scaling test, which I'm going to show next, which produced a parallel scalability of more than 95% on almost 10,000 Frontier nodes. And you have to consider each of those nodes has 8 of those AMD GPUs. So it's a massive number of GPUs that have been used in this test. So this is a full scale system benchmark. And you can see with this in this brown line in this diagram how the HIP-aware MVAPICH improved performance with respect to the native or a non-HIP-aware version, and it gives you improvements between 10 and almost 20%. Another test that was carried out was on Vista, also with AWP and MVAPICH. And you can see here the parallel efficiency as a function of a number of nodes. So those nodes are a lot faster. So it was carried out for up to 200 nodes. And you can see that you're getting a parallel efficiency is also well above 90%, which is really great. And in this case, the improvement from CUDA-aware to native MPI was only a bit more modest, in the range of about 3.5%, which you can see, which is shown in the dashed line here. So that's the same result again in the table. So I'm gonna wrap up here. So in conclusion, AWP is a highly scalable wave propagation code that is capable of simulating the wave propagation during large earthquakes at the resolution that are relevant to seismic hazard. And the code has been ported to leadership class systems, which are accelerated by NVIDIA GPU or AMD GPUs using the CUDA or HIP protocol. And recent additions to the code account for seismologically significant phenomena. So in particular, nonlinearity. So we have the simple J2 Drucker-Prager type nonlinearity, and the more realistic, computation expensive Ivan type nonlinearity. Other developments include scattering on small scale heterogeneities, or scattering by topography, which has also been implemented in a different branch of the code. We addressed computational challenges that arose from implementing those features by improving the algorithm. For example, as I mentioned, the yield factor interpolation, by changing the computation schedule, or on-the-fly computation of physical properties. And another massive improvement, of course, is the introduction of a discontinuous mesh. And recent production simulations, such as the shakeout scenario with both J2 and Ivan type nonlinearity, and also the Landers earthquake, confirm the importance of nonlinearity in the shallow crust. And AWP achieved impressive performance and scalability with MVAPICH and on OLCF Frontier and TUG TSCC Vista. So yeah, I want to thank all the people who collaborated on this project, especially the HPGOC team, which was involved in implementing the HIP version, also collaborators from different institutions, and the agencies that gave us the computing allocation and the funding. Thank you.
Let's give big hand. Any questions for Daniel? Here or remote? So I think I have a quick question, Daniel. I think your frontier number looks very impressive. You ran up to 10,000 GPUs, am I right?
Yes,
On the
that's
AMD
correct.
frontier. Did you see, I mean, performance scalability is one thing. Today, earlier, we heard from like Manoj about reliability and all. Did you see any issues when running these large scale simulations on frontier?
Maybe Ifan would be better for answering the question.
When you ran these large scale simulations, I think it must be taking multiple hours, am I right? Did you see any failures or because of the GPUs or because of your code?
I didn't carry out this test myself, so I'm
Okay.
not familiar for this frontier system if there was any failures.
Okay, no failures. That's good.
So Ifan tells me there were no failures and it worked well on frontier.
Okay, sounds good. So there is a question online from Benson. The question is, do you expect to do a port for Intel GPUs?
I mean, there is a CPU version of the code that is also being maintained, but less actively. So that version has either non-linearity, it doesn't have the discontinuous mesh. So often that version is interesting to us when we try implement new models. So I did the either non-linearity first with the CPU code, just as a prototype.